Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we have been looking at various functional units. In the previous lectures, we also looked at the memory system in great detail. So, we looked at how the main memory is organized, we looked at the cache design, we looked at different mapping techniques in cache performance, and we also looked at virtual memory. So, having looked at the control unit and the memory unit, the other major unit that we need to understand is the input output unit. So, that is what we will look at starting from the class today. In today's lecture, what we will be looking at is the basic characteristics of an I/O system, how the interface is handled, and a little bit on how the interrupts are handled. So, if you look at an I/O subsystem as such, so you can see how the entire set of devices are in place. So, we have the processor, we have the cache, and then the main memory. Now, the processor and the cache are connected to the main memory by means of some kind of an interconnection mechanism here, normally the memory or the I/O bus. So, the memory as well as different I/O devices are connected by means of this some interface that we have in between, typically which is called as the typically we have the bus as the interface system that is used. So, we have this memory and I/O bus which connects main memory and the different I/O devices to the processor and the cache. Now, if you look at the different devices, we have shown a few devices here. It could be a hard disk, it could be some graphics device, display device, it could be a network that is used, and you normally have some kind of a controller for each of these devices which connects to the processor through this I/O bus. So, you would have different I/O controllers, input output controllers which connect to the actual I/O devices, and this in turn these input output controllers in turn would be connected to the processor by means of this I/O bus, and they will also have some mechanism by which they are able to send some messages to the processor. Typically that kind of a mechanism would be what we call as an interrupt system. So, this is basically what you would see in any computer system, that is you will have this interface in between which connects these different devices. So, what we need to understand in terms of input output systems therefore is how exactly this kind of an interface system is designed, and how is it that the processor is able to talk to the input output controllers, and how is it that the input output controllers are able to talk to the processor. Okay. So, this is what we need to understand in terms of the I/O subsystem design. So, now coming to this interconnection that we are talking about. So, what is the necessity that we have? We want an interconnection between CPU, memory and the I/O controllers. So, normally what we have, as I said, is some kind of a shared communication channel. The communication channel which is commonly used in this kind of a situation is a bus. Now, what is a bus? It is essentially a parallel set of wires for transferring data. Okay. So, it is for it could have data, it would also have other control lines, but essentially you can look at bus as a parallel set of wires which is used for transferring data. Sometimes this bus itself can become a bottleneck because it is a shared communication channel. Okay. That is something that we will need to address as we look at the design of an I/O subsystem. Okay. There could be other factors which also limit the performance, which could be in terms of the wire length, the number of connections that we have and so on. So, more recent alternatives, we have high speed serial connections with switches like the way it is used in networks. So, that is also a possibility that we have which is coming up as a more recent alternative, but typically bus is a very commonly used interconnecting component. So, if we understand how the bus operates, it would help us to understand how many of the the I/O devices actually get connected to the processor. Okay. So, let us look at the details of bus in let us look at the bus in a little more detail. Now, if you look at bus essentially is a communication path for the transfer of data. Now, it also includes lines to support interrupts and arbitration. We will come to what we mean by interrupts and arbitration a little later, but you can look at this as transfer of data along with some control lines. Okay, that is one way to understand what a bus is. A bus protocol is something that we also have, which is a set of rules that governs the behavior of various devices connected to the bus as to when to place information on the bus, when to assert control signals and so on. Okay. When is it that when is the data can be placed on the bus, when is it the data can be taken from the bus, all these things are controlled by means of a bus protocol. So, whenever we have any bus that is designed, we would normally have a protocol also that goes with it, which we need to understand to see how exactly data will be transferred from the bus and to the bus. Okay. So, when we talk of bus in the context of a processor, normally we talk about processor memory bus and I/O buses. So, you can look at this as two different types of buses, processor memory bus and I/O buses. Now, processor memory buses are typically short in the sense that the length of the buses are short and they are normally high speed, and the design is such that it is normally matched to the memory organization. Okay, that is through the you can say in a sense to the speed of the memory and to the way in which the memory is organized. So, this is how the processor memory buses are normally designed. And then in addition to that, we also have I/O buses. Again, normally I/O buses tend to be longer and allow for multiple connections, that is, you have different I/O devices that you will have to connect. So, the I/O buses are normally designed to have multiple connections, that you should be able to connect different I/O devices. And the multiple connections and these different I/O devices are of different types. So, we need to have buses which can support these different types of devices. So, in order to support different types of devices, we normally have certain standards, so that you have this interoperability in place. Okay. So, you have I/O buses specified by standards for interoperability, and to connect to the processor memory bus, you normally have some kind of a bridge that is used. So, the I/O bus itself can be connected to the processor memory bus through a bridge. Okay. So, this is basically the system that you normally have, that is, you will have a processor memory bus which connects to the memory, and then this processor memory bus can be connected to an I/O bus by means of a bridge. Okay, this is a typical setup that you could have. So, if we look at this figure here that we just saw, we talked about a common memory I/O bus over here. This is also one kind of a configuration that we could have, a common configuration where we have one bus to which both memory and I/O devices are connected. The configuration that we talked about just now is one where I am having two buses, one for the processor memory and one for the I/O bus. Both these types of configurations are common in use. Okay. Now, coming to the bus lines that we have can be generally grouped into three types: data, address and control. Okay. So, let us look at what is specified by each of these. Now, when we talk of data and address, it is self-explanatory in the sense that data lines will be the ones which are going to carry the data, address lines are the ones which are going to carry the address. Sometimes you could have both data and address as one common line, in which case we say that the address and data lines are multiplexed. So, that is a possibility. You could have one common set of lines which is used to transfer data as well as the address, or you could have separate lines for data and separate lines for address. What we need to really understand is the kind of control signals that are available. Okay. So, let us look at control signals. What do we expect the control signals normally to specify? One thing that we want to specify is whether it is a read or a write operation, because it could be reading from the bus or you could be writing to the bus. Okay. So, whether it is a read or a write operation, that needs to be specified. Second thing that we need to specify is the size of the data, the required size of the data, okay, especially when several operand sizes are possible, that is whether we are reading a byte at a time or a word or a long word and so on. Your bus itself may be supporting a long word, but using the long word bus you may actually be transmitting only a byte or a word, in which case you need to specify what is the size of the data that is being transferred. Okay, this is the second thing that we need to specify. Third thing that we need to look at is timing information to indicate when the processor and the I/O devices may place data or receive data from the bus. So, if you look at the way it is organized, you can see that the bus stands in between the processor and the I/O devices. So, the processor is going to place data on the bus and the I/O device will have to take the data from the bus, or the I/O device is going to place data on the bus and the processor has to take the data from the bus. Okay. So, but we need to have some kind of a timing information as to when a processor or an I/O device may place data on the bus and receive data from the bus. So, all this has to be specified by means of these control signals. Okay. So, to do this specification of control signals, normally there are two schemes that are used for timing. One is called an synchronous bus and the other is called as an asynchronous bus, depending on whether the timing is specified synchronously with respect to some kind of a clock or whether it is done by means of some asynchronous signals. Okay. So, we have synchronous buses and we have asynchronous buses, or we have synchronous timing and asynchronous timing for specifying this control information. Okay. So, so overall with respect to bus signals, you can say that we have data lines which carry address and data, which may be multiplexed or separate, that is the address and data may be multiplexed or separate, and then we have control lines which indicate the data type, size, and which are used to synchronize transactions. And if it is synchronous, we will have normally a bus clock, and if it is asynchronous, we have a different mechanism. The different mechanism that we have normally is some kind of a request and acknowledgement kind of control signals for handshaking. Now, this is a term that is normally used whenever we talk about interfacing I/O devices. Handshaking is a term that is normally used. So, when we talk of handshaking, it is normally used in the context of an asynchronous transfer, and it is similar to the handshake that we normally do, right, that one person puts out the hand and then another person puts out the hand in response to that. So, you can look at the same thing happening here, one device puts out a request and the other device responds by giving an acknowledgement. So, request and acknowledgement is like doing a handshake. So, which is why it is normally referred to as a handshake set of operations or handshake signals. So, so overall this is what we have. So, we have a bus and the bus could be a synchronous bus or it could be an asynchronous bus, and if it is a synchronous bus, then we use a bus clock and we do the timing with respect to that bus clock. If it is an asynchronous bus, we do the timing with respect with the help of some special control signals which are used for this purpose. So, now we will take a look at how synchronous how data transfer is done in a synchronous bus and in an asynchronous bus. Okay. So, let us look at the synchronous bus first. So, as I said, in a synchronous bus, the one which governs the timing is the bus clock. So, that is something that we will always keep in mind. So, you will have your bus clock which is going to determine when exactly the data transfer is going to take place. So, whenever you have a clock, you have an on time and an off time, and we have a rising edge and the falling edge of the clock. So, these rising edge, falling edge edges as such can be used for determining what will take place and what will take place and when it will take place. Okay. So, for instance, let us say we have a system like this. So, you have this bus clock and then I have my address and command, okay, line signals, and then I have my data signals. So, the way you could do things on this is you can have the master or the one which is driving the bus, the one which is now sending data onto the bus. Normally, we use this term called master and slave with respect to the bus. So, what we mean by a master is the one which is placing data on the bus, and the slave normally is the one which is receiving data from the bus. So, anyone could be the master and anybody else could be the slave, depending on who is doing the data transfer. Okay. It could be the processor that is the master and the I/O device could be the slave, or the I/O device could be the master and the processor could be the slave which is receiving the data. So, it could be either way. So, depending on whoever is doing the transfer, we will just refer to that person as the master. Okay. So, what can happen in a synchronous data transfer is that at this time t0, that is at the beginning of the clock pulse, okay, the master could place the device address and the command on the bus, okay, and indicate what kind of an operation it is. So, in this case it is a read operation, for instance. So, it provides this command signals, the address and command is provided at t0 placed on the bus. Okay. So, we know that at t0, that is at the rising edge of the bus clock, the address and command are placed on the bus, and then at t1, which is the falling edge of the clock. Okay. So, you can say that at this point of time, the addressed slave will place the data on the data lines. This is a read operation, remember. So, we are trying to read data from the device. So, the master sends out the address from which the device from which the data has to be read, and also specifies the command that it is a read command. So, now in response to the read command, the slave, depending on the address, knows that it is the one that is being addressed. So, it responds to it and places the data on the data lines. Okay. So, once the data is placed on the data lines, at time t2 now the data is available. So, the master now can take the data from the bus and strobe it into its input buffer. Okay. So, normally we say the master strobes the data on the data lines into its input buffer for a read operation. So, you can see now how just with respect to a clock you can specify specific instances when certain operations can take place, and that can be used by both the devices to transfer the data from one to the other. We will take a short break now and come back and continue with this. Welcome back after the break. So, we were just looking at how data transfer takes place on a synchronous bus. So, we looked at how a read operation can take place, right. So, similarly, so let us look at how a write operation would take place. So, in case of a write operation, what is it that is to happen now? The master now will place the data on the bus along with the address and the commands at time t naught. Okay, that is at this time t naught, not only the address and command, but the data also will be made available here. So, now the slave will strobe the data into its input buffer at time t2. Okay. So, the slave now has the slave, remember it is a write operation. So, the slave now has to take the data from the bus and put it into its input buffer. That would happen at time t2. Okay. So, for a read operation there are three things which is done, which is that you place the address first, okay, and then the slave will place the data and then it is read by the master again. Okay. Now, in the case of a write operation, the placing of the data and the address and command are combined together, and at time t2 writing of the data by the master would be completed, because now the data would have been copied into the input buffer by the slave. Okay. That is how a write operation will take place. So, now once the master places the device address and the command on the bus, we see that there is a large time that we have between t0 to t2. Now, why do we have this time? It is because it takes time for the information to propagate to the devices. So, remember that the bus is actually a physical connection, right, it is a set of wires. So, now time it takes time for data to propagate along this is the signal actually to propagate along these wires. So, so we need to give some time for the propagation to happen, which is why you have this t0 to t2, this time that needs to be specified. Okay. Now, normally this time will depend on the physical and the electrical characteristics of the bus. So, that is something that was determined by what kind of electrical characteristics are there, and it depends, it is basically a design decision. Okay. Okay. So, now when we design a bus which is a kind of a standard bus which needs to be used by any device, what we need to keep in mind is that we need to give enough time for all the devices, okay, to decode the address and the control signals, so that the address slave can place the data on the bus. So, remember what we assumed here was that we said we place the address on the bus and we said that the slave will just respond to that. Now, how will the slave respond to that? It should first know that it is the one that is being addressed. How will it know that it is the one that is being addressed? By looking at the address. So, it has to decode the address, identify that it is the one that is being addressed. So, it takes some time for this decoding to take place. Okay. So, that is what we mean when we say that all the devices have to be given enough time to decode the address and the control signals, okay, so that the address slave can become ready to place the data on the bus. Okay. So, this width of the pulse. So, we said that we have a clock and we said that something happens at the rising edge, something happens at the falling edge. So, what exactly should be this time? How do I determine what is the width of this pulse that I have? That is t1 minus t0. What would it depend on? You can see that it will depend on the maximum propagation delay between two devices which are connected to the bus, okay, and it also has to take into account the time taken by all the devices to decode the address and control signals, so that the address slave can respond at time t1. Okay. So, this time, that is the propagation delay for your signal that has been placed by the master to go to the slaves, to all the slaves, and then the time that it takes for each of the devices to decode the address and control signals, and for it to respond at time t1. Okay, it will have some time that it takes in order to get the data and put it on the bus. So, that also, that setup time also has to be taken into account. So, t1 minus t0, this width of the pulse is dependent on these two factors. Okay. And at the end of the clock cycle, that is at time t2, we said the master will strobe the data on the data lines into its buffer if it is a read operation. If it is a write operation, then at the time t2, it will be taken by the slave and put into its buffer. Okay. So, what do you mean by strobe? Strobe essentially means to capture the values of the data and store them into a buffer. So, normally we use this term called strobe, a read strobe or a write strobe as we refer to it. Okay. So, the strobe normally means that is when the data can be captured and stored into the buffer. Okay. So, when we do this again, the data, when data is to be loaded into a storage buffer register, the data should be available for a period which is longer than the setup time of the device. So, since I have to store it into the buffer, remember whenever we store into any buffer, which is essentially any memory component, there is something called a setup time and a hold time. So, you need to therefore make data available before the setup time, and you need to hold the data for a little time which is more than the hold time. Okay. So, both these have to be taken into account when you are deciding on the clock pulse width. So, what is my T0 to T1 and how much is my T1 to T2? All these things, this T0 to T1, T1 to T2 has to be decided taking into account all these factors that are there. Okay. So, that is how we need to look at designing the frequency of the clock for the bus. Okay. Right. So, width of this pulse T2 minus T1 should be longer than these two things: maximum propagation time of the bus plus the setup time of the input buffer register of the master. Okay. So, these are the two things that we need to consider into account. So, for T0 to T1 we have a requirement, similarly from T2 to T1 we have a requirement. So, these two put together will determine what is the overall pulse width, and it will also determine what is the frequency of the clock that can be used. Now, the next point that we need to also remember is what I told you about the hold time. Okay. So, remember that signals do not appear on the bus as soon as they are placed on the bus due to the propagation delay in the interface circuits. Second is signals reach the devices after a propagation delay, which depends on the characteristics of the bus. Remember, there are two different propagation delays we are talking about over here. One propagation delay is the delay that it takes for the signal to go on the bus itself, and second is there is a delay for the which is there in the interface circuits of the input output device that you are talking about. Okay. So, from there, for it to be, before it can be placed on the bus, again there will be some delay. Okay. So, both these delays have to be taken into account. Okay. And data must, as I said, remain on the bus for some time after T2, which is equal to the hold time of the buffer. So, we have the setup time, which is the time before the clock that it should be there, and some time called the hold time after the clock for which the data should be available. Only then you can make sure that the data is successfully written into the buffer. Okay. So, these are the things that we need to keep in mind with respect to the timing for the synchronous bus. Okay. So, you can see all these things captured in this figure over here. Okay. This is our bus clock, right, that we have. Now, so this is our address and command. Okay. So, the address and command will appear on the bus, as you can see, a little later, okay, TAM, a little later than this edge of the clock. Okay. This is when it will actually appear on the bus. So, it will appear on the bus, and it will have to be on the bus, as we said, for a little time after the data has been strobed in. Okay. So, you can see that this value remains on the bus until the end of the clock, and also for a little bit of time after the clock. Okay. That is what you need to remember over here. Okay. So, this is placement of the address and data, address and command. Now, if it is a read operation, when is the data going to be available? Data will be available sometime after the after the address and command have been placed. That is, you can see this, you can see this over here, address and command. Let us say this is TAM is when the address and command are placed on the bus. Address and command will reach the slave after some time. Okay. So, this is how things are, the upper part is how things are as seen by the master, and the lower part is as things are as seen by the slave. Okay. So, the master puts out the data and the address and the commands at this point of time. It will propagate on the bus. So, the slave actually sees it after some point of time. So, only after it sees the address and the command, it will decode and all that, decodes the address, finds that it is the one that is being addressed, and then picks up the data and makes the data appear on the bus. Again, you can see with respect to the falling edge of the clock, which is our T1, after some time is when the data will be available on the bus. So, data becomes available at this time TDS, which is when which is a little after T1. Now, this data which is there on the bus is being put by the slave. Okay. Now, this again has to propagate to the master. You can see that it will also take some time. So, at this time it is available on the bus, it has been placed on the bus by the slave, and at TDM, right, this is at this point of time is when it actually reaches the master. So, when this reaches the master, okay, now at time T2 it will be taken in by the master. So, you can see that it reaches over here. So, this time over here, that is between TDM to T2, will be equal to the should be at least this time TDM to T2 has to be greater than the setup time that is required for this master to read in the data. And similarly, you can see that the data is held onto the bus for some more time, which is definitely greater than the whole time that is required for the master to take in the data. Okay. So, you can see that the address does not change before that, the data does not change at this point of at T2. It is valid before T2, sometime before T2 and valid for some time after T2. Okay. So, you should see that we need to take into account all these delays that will be there. Okay. So, and keep in mind that the actual transfers will take place, okay, not exactly at T2, but a little before or after T2, okay, depending on the delays and the setup time and the hold times that we have. Okay. So, what we need to remember from this figure basically is that you need to understand what is happening from the master side, and we also need to understand what is happening from the slave side. Okay. And both these we need to understand in order to realize when exactly the data transfers will take place. Okay. So, this is how data transfer takes place in the synchronous bus. Now, we looked at the entire data transfer as taking place within one clock cycle. So, we said that the clock period T2 to T0 must be such that the longest propagation delay on the bus and the slowest device interface must be accommodated. Now, the reason we say this is that we have different devices, and different devices may have different setup times and different hold times. So, whichever is your slowest device, that device should be accommodated, okay, and so automatically all the other fast devices will be accommodated. So, what happens is when we have one common clock that is used and we want that is used by all the devices to transfer data, we have to make sure that the clock is able to accommodate the slowest device. Okay. So, it forces all the devices to operate at the speed of the slowest device. So, this is one point that we need to keep in mind. Second thing that we need to have in mind is that what we have looked at right now is we have assumed that the data becomes available, whether it is a read or a write operation, the slave device is responding to it immediately. Okay. But it is possible that the device could actually have failed and never actually responded. Okay. In these cases, what do we do? What we have to do in these cases is that we use some additional control signals. So, most of the buses will have some additional control signals to represent a response from the slave, okay, and in which case the same control signal can be used for both purposes. One is to inform to the master that the slave has recognized the address and is ready to participate in the data transfer operation, and second is to adjust the duration of the data transfer operation based on the speed of the participating devices. That is, I do not have to the entire operation need not take place within one clock cycle, but you could have multiple clock cycles for the data transfer to take place. Okay. So, in that information as to in which clock cycle what is taking place is done with the help of these additional signals. So, we will see how that is done. So, you can see here I have a clock, the bus clock running through, okay, and say at the first clock cycle the address and the command are placed over here on the bus. Okay. So, the address and command are placed over here. So, let us say for instance the data becomes ready only after 2 clock cycles, right. In clock cycle number 1 I am placing the address, only in clock cycle number 3 it becomes available. So, now how is this informed? This is informed by having this special signal here called slave ready. Okay. The slave ready signal you can see becomes active, okay, only in this clock cycle number 3. So, when this signal becomes active, this is an indication, okay, that data is now available on the bus. So, only when the slave ready signal is active the data is made available and that is read by the master. Okay. So, you can see that you can have multiple clock cycles. So, a slower device may take more number of clock cycles, a faster device may finish it off in one clock cycle. So, you can see that by going in for this additional control signals, you can accommodate both faster and slower devices and not compromise on the timing. Okay. And second thing is that if a device is not ready, it would not have put up this slave ready signal. So, you will also know that it is not responded. So, both these problems can be solved with the help of this kind of additional signal that we use. So, to summarize, what we have looked at today essentially is basics of how an interfacing can be done. So, we have looked at a very standard interface called the bus. Okay. So, interfacing devices through a bus. So, we looked at what are the different types of signals that are normally used in a bus, address, data and control signals, and different types of buses, the IO bus, memory bus, and then we talked about synchronous and asynchronous bus. So, we have particularly looked at synchronous bus in detail. So, it is a clock based system. We have looked at different timing with respect to a read and a write operation for a synchronous bus. So, questions to review today's content. Question number 1, what is a bus? Question number 2, can the IO bus be different from the memory bus? Question number 3, what is meant by synchronous transfer? Question number 4, list the steps with timing for a write operation to take place on a synchronous bus. Thank you.